Welcome to
Nay.
Do it.
Channel Everyone. This is episode 2020-60404. Okay, so today we are diving into a paper that tackles a very modern problem. We all love how smart our recommendation systems have gotten. Right, they suggest videos, products, music, by looking at what we clicked and also the actual content. The images, the text, that's a multimodal system. But what happens when you need to make it forget asterisk something? Like, if a user deletes their data or a problematic item needs to be removed.
Right, it's not just a privacy checkbox. Full retraining from scratch every time you need to delete something is computationally insane. So the field uses approximate unlearning, trying to efficiently reverse the influence of specific data without breaking everything else.
Exactly. And the common approach has been to apply a kind of uniform, reverse update across the entire model, a one-size-fits-all reversal. But this new paper argues that's fundamentally flawed for modern multimodal recommenders.
Flawed. Why? Because the influence isn't spread out evenly.
Precisely, the paper identifies 3 key places where the influence of the data you want to forget is concentrated. Bottlenecks. First, the ranking behavior. The system might still subtly favor that deleted item in its rankings. Second, the modality branches. The influence might be stronger in, say, the image processing branch than the text branch. And third, across the network layers themselves. Some layers are more sensitive to the deletion than others.
So applying a uniform reverse update is inefficient. It's like trying to cool down a hot room by turning the air conditioning on in every room of the house, instead of just targeting the room with the oven that's on.
I love that analogy. So, what's the solution? How do you do targeted cooling?
They propose a framework called TRU, Targeted Reverse Update. Instead of a blind global reversal, it performs 3 coordinated interventions. 1. A ranking fusion gate. This actively suppresses any residual influence of the target item in the final ranking score.
Then, branch-wise modality scaling. This applies different strengths of the reverse update to each modality branch, like image, text, to preserve the good representations you want to keep in the unaffected parts.
And the third.
Capacity-aware layer isolation. This identifies which specific layers in the neural network are most sensitive to the deletion and focuses the update there, leaving less sensitive layers more alone. It's a plug-and-play framework you can add to existing models.
The results are compelling. Across different model backbones, datasets, and unlearning scenarios, TRU achieved a better trade-off. It forgot the target data more thoroughly, while better preserving the performance on the data you wanted to keep. Security audits showed its behavior was closer to a model fully retrained from scratch without the deleted data.
So it's more precise, more efficient, and more secure. This feels like a move from a blunt instrument to a surgical tool for AI maintenance.
Exactly, it acknowledges the complexity of these systems and designs the unlearning process to match that complexity. It's a more realistic approach for deployment.
Fantastic. Thank you both for breaking that down. It makes a lot of sense.
Thank you.
Thanks.
And thank you for watching. We'll see you next time.